In this example, let us look at an unbalanced assignment problem. One of the main assumptions of the Hungarian method is that the assignment matrix is of square shape. That is, the number of rows equal the number of columns, so that one-to-one match is possible. When the number of rows are equal to the number of columns, the resultant problem is called a balanced assignment problem. And if they don't, then it is called an unbalanced assignment problem. Unbalanced problems occur when the number of machines are either more than the number of jobs, which would mean that some of the machines may remain idle, or the number of jobs are more than the number of machines, which would mean that some of the jobs would not get allocated. To solve such problems, a dummy row or column equal to the difference between the rows and columns are inserted with zero cost. And once the problem has been balanced by the introduction of dummy row or column, the usual assignment routine can be applied. So let us now go through the problem at hand. A departmental head has 3 subordinates and 4 tasks for completion. The employees differ in their capabilities and the tasks differ in their work contents. With the performance matrix given below, which 3 of the 4 tasks should be assigned to the subordinates? So assume that you are a departmental head and you have 3 subordinates and 4 tasks have been given to you that needs to be assigned to the 3 subordinates. The question here is that only one task can be assigned to one subordinate. And how do you minimize the overall cost? So here, as you can see in the matrix, A, B, C and D are the 4 tasks, and 1, 2 and 3 are the subordinates. You can see the time noted in the matrix. So the first subordinate takes 9 hours to complete task A, takes 8 hours to complete task B, 20 hours to complete task C, and 21 hours to complete task D. If you compare this matrix with the previous problems that we have looked at, you'll see that there are 4 tasks and 3 subordinates. So this is a perfect example of an unbalanced assignment problem. So let us look at how we can go ahead and solve this. The step 1 would be to express the problem in an n by n matrix. So let's first note down the matrix. Now, since this is an unbalanced problem, we'll have to add another column to make it balanced. So let's add column number 4 here, and we'll assign 0 hours to this column. So let's put zeros for all the tasks. So now let's understand why we are assigning zeros for the dummy subordinate. Now, the main objective of the whole problem here is that we want to assign tasks A, B, C and D to 3 subordinates, 1, 2 and 3. So basically we can only assign 3 tasks out of these to the 3 subordinates. We have to assign these tasks to 3 subordinates in such a way that we minimize the total number of hours. So first objective is that we find out which task should be assigned to which subordinate, and since we can assign only one task to one subordinate, we also will have to identify which task remains unallocated. Now the idea here behind assigning the zero costs to subordinate number 4, which is a dummy subordinate, is that one of the tasks would turn out to be more time consuming if assigned to subordinates 1, 2 and 3 as compared to the other tasks. Now that particular task will be assigned to the dummy subordinate, or in other words, remain unallocated. So now let's move to step number 2. Now let's minimize the complexity of the problem by first deducting all numbers in a row by the smallest number in the row. This way we can then target the assignment of zeros for the tasks to subordinate combination. So now let's go row wise and see which is the minimum number. So for A we have 0. Okay, so we don't need to deduct anything. B also we have 0, C also we have a 0, and D also we have a 0. So basically for step number 2 we can't do anything. So let's copy the matrix as it is. Now let's move to step number 3. In this step, let's repeat the same steps done in step number 2, but this time we'll go column wise. So for first column, the minimum number is 8. So let's deduct 8 from each of the numbers in this column. So we'll get 1, 0, 12, 13. Same for second column. So minimum is 12. So let's deduct 12 from each of the numbers. So we get 0, 1, 0, 3. Same way for third column. The minimum number is 11. So after deducting we'll get 0, 6, 2, 6, and for 4 it's already zeros, so we'll just copy the column as it is. So at this point let's find out if we have already reached an optimal solution or not. So let's move to step number 4 to find that out. So in step number 4, let's first copy the matrix that we had received at the end of step number 3. So now in order to find out whether we have reached the optimal solution or not, we will try to cover the maximum number of zeros by the minimum number of straight lines. If the number of straight lines is less than the number of rows and columns, that means that the optimal solution has not been reached. But if the number of straight lines is equal to the number of rows and columns, that would mean that we have already reached an optimal solution. So let's first go row wise to find out if we can find any row with 4 zeros. So we don't have first, second, third and fourth. Okay, Now let's go column wise. So we do have column number 4, which has 4 zeros. So let's cut this column with a straight line. Now let's again try row wise to see if we can have 3 or more. So we don't have any row which has 3 or more. Let's go column wise. Again, columns we have 2, but none with 3 zeros. So now let's try row wise again for 2 or more. So we have the first row which has 2, so let's deduct this row. Second we have 1, third we have 1, fourth we have none. So let's try the same thing column wise. So we have first column only 1, second column only has 1, third column doesn't have any. Now again let's try row wise with 1 or more. So we have, for B we have 1, so let's draw a straight line. For C also we have 1, so let's draw a straight line. So here you can see that the number of straight lines equals the number of rows and columns. So that means the optimal solution has been reached. So now since the optimal solution has been reached, we can now make our assignments of tasks to the subordinates. So let's move to step number 5. Now let's copy the matrix. Now to make the right assignments, let's go row wise to find if we can find any mutually exclusive 0 for that row. Same thing then we'll repeat for column wise. So the first doesn't have, second has 2, third has 2, and fourth has 1. So let's assign 4 here. Now since 4 has been assigned to D, 4 cannot be assigned to any other task. So let's cross the other zeros for that column. Now let's repeat the same steps, but this time we'll go column wise. So first column has 1 0, so let's assign this 0. Now there is no other 0, so this is the assignment. Now second column has 2 zeros, so we'll leave this for now. Third has 1 0, so let's assign this 0 here. And since A has now been assigned to 3, they cannot be assigned to any other subordinate, so let's cut this 0. Now let's again go row wise. First is already assigned, second is already assigned, third we have a 0 available, so let's select this, and there are no other zeros, and D is also already assigned. So now we have our final assignment, that is A is assigned to 3, B is assigned to 1, C is assigned to 2, and D is assigned to 4. So what this means is that D is the one which will remain unallocated. You can then reach out to the main matrix and find out the actual hours. So A to 3 is 11, B to 1 is 8, C to 2 is 12. So your total is 31 hours. So this is the final solution.